Okay, let me ask this way. Um, what scenarios can you think of where you need to actually use clustering methods? Let's think about a scenario where you need to like use clustering. It doesn't need to be anything fancy, just whatever comes to your mind. Okay. Atif says identifying modal state from EEG data. Okay, Atif, maybe you need to clarify it a bit, because I know a little about EEG data, but some people might not. Mina Hill says checking trends in data, like what's most popular. Okay, actually we have done this in the previous parts, Mina Hill. Like checking trends is something that we've already done, and I'm not gonna say we won't use clustering for these purposes. Barnacle says when you need to decide what type of class something is, well, that's actually the first guess that you have from the name clustering. So yeah, a bit more complex, a more complex example needed. Mahdi says recommending movies in Netflix. Yeah, that's actually a really good problem that can be solved with clustering, because let's read other comments and then I will let you know. Tim says to group unlabeled data into similar groups. Yeah, that's actually the definition of clustering. Kane says, I guess we use clustering when we have unlabeled data and want to discover which items are similar to each other. Yeah, that's also the definition. Cohen says, I wasn't at the lecture, but I'm thinking political spectrum. That's also a good idea. So to make it simple, Mahdi actually gave us a really good example. Let's say you want to make a decision and you're not sure about the parameters, okay? Like in feature engineering, we tried to turn our data into some more meaningful features where we could actually measure the strength and the effect of those features. Like we could see how each person or each data point is positioned when we look at the dataset through the features lens. Okay, so let's say in the Figma example, we realized that, I'm just giving an example, it might not be accurate. We realized that if a project, if somebody's been working with the project in the past 30 days, there might be a higher chance of using like a specific feature on the platform. Clustering is used where we are not actually sure about the feature or about the specifications that lead to a behavior. Okay, so recommending here is one example. You might not actually know for an exact user which movie to show them when they have finished the movie. Okay, they have watched, let's say they have watched Project Hail Mary, and you want to decide 5 movies to recommend to them for the next weekend. They're gonna watch like Netflix or like any streaming service. You don't exactly know. You might not know what features result to their decision. However, you can look at people similar to this specific person. So you look at the cluster of users. Okay, so you put them into groups, and instead of like predicting one single point, you know that the cluster itself behaves in a specific way, and you know that this user who has watched Project Hail Mary is similar to like other users within the same clusters, and from that cluster, you know, those who have watched Project Hail Mary, they're probably like interested in like Arrival or Interstellar or like any other movies. So it's actually for the time when we want to make a decision, but in an indirect way. What we're gonna do today, as you can see on my screen, is that we have a data set of some businesses. This data set is actually imaginary, and I'm gonna put it on Discord. I'm gonna put this scaffold and the data set and the libraries that you have to use for this lab on Discord under the additional resources. So let me put this here. Just give me a second. I'm gonna upload them quickly. Unfortunately, I haven't created a repository for it yet. Okay, so this is here, business locations and requirements. What you need for today's lab. Okay. So you can have the data set. The scaffold just consists of some pseudocode, and I will be working step by step. I will be completing it step by step just to show you some of the libraries that you can use for clustering purposes and the difference between different clustering methods. And since some of you are not really comfortable using Discord, I'm gonna attach the very same files to the announcement that I have published for today's lab. Okay, this, and this. Okay, these are the files you need for your lab today. So the data set, the scaffold, and the requirements, the Python requirements. Okay, so here's the problem that we are tackling today. We have the data set, which is a new kind of data set. It's a GeoJSON, which this is a type of a data set that you will be using when you're working with like city data, municipality, yeah, those sorts of data. They consist of location and different features, and they're more complex than the ordinary CSV. And somebody with a huge amount of money has given you this data set and is asking you to help them find a neighborhood and a business category where they can make good money and meaningfully contribute to the local community. Okay? So this is what they have asked us. And I guess it's a really common problem, really common thing that we will be facing. So first of all, let's take a look at the data set. Is the problem definition clear here? Like, do you have any questions? You've already seen it while I was sharing my screen, so I just explained it. Everything's cool? Okay, I assume no reaction means everything's cool. Okay, let's take a look at the data set. So your data set, instead of a CSV, is in the format of a JSON. Okay, so it's technically a list of dictionaries. Okay, this is the curly brackets tells us this is a dictionary, and it has two parts. One part is the location of the, actually three parts. One is the type of the location, then is the location of the coordinates, and the properties of that location, like the neighborhood, the category, the subcategory, and some numbers about like the floor area, daily foot traffic. Yes, please. I can actually do it really quickly right now. Like, I thought I had uploaded them on GitHub, but I hadn't. So I just thought, I actually, you are meant to follow along with this lab, because this is pretty much similar to the assignments that you're gonna have. Okay, this is like a simplified version of your assignment, and learning from the previous sessions, I think we might not be able to cover the whole thing. So you might need to like proceed with the rest of it. So just give me a second to create the repository, lab 5 clustering. Okay. Create a repository. And I'm gonna put the files here. Business locations, requirements. Okay. Commit changes. Okay. And here's the link to the repository. Okay. This is private. Let me just make the repository public. Change to public. I want to make this public. Public. Okay, it's also public right now. Okay. You're welcome, Hint. You're welcome. Okay. Now you have the codes on the repository. You can download them. Okay, so here's the problem. Here's the data set. So you've all, I hope that you've all understood the data set. So we also have the annual revenue. We have the community impact score. Somebody has like magically measured this number, which is a summary of the community impact that this location has. Again, this is an imaginary data set. First of all, we're going to see what libraries we're going to use. Just as usual, we have NumPy, Pandas, Matplotlib, Seaborn, scikit-learn. However, based on the new tools that you've learned last week, we're going to also use these libraries. Okay, so k-means is for k-means clustering, DBSCAN is for DBSCAN, high definition, and these three are for dimensionality reduction, dimension reduction. Okay, and you can just ignore these, but this one is important. Last week when we were developing a model together, where we were creating a realist model together, we had a random number to for the model to start learning from the currently existing data sets. Let me see if I can find the code. It was feature engineering. Let me see. Where was it? Okay, I cannot find it right now. But if you remember it, I think it was Tim who asked about like the number that we were using there. I'm not sure, but this number here, this random state here, is used to tell the model how to learn from the existing datasets. Okay, so we define it as a global variable, so that all through our code we use the same number, so that we all get the same results. Okay, so if you are also coding with us, I suggest you to do the same thing. Okay, because That way we will see the same results. If you change this number, your results might be a bit different from like what we see here in the lab together. Okay, just have this at the back of your mind. Okay, I have to close some tabs because my device is lagging. Let's close Discord. Okay, just keep the ID open. Okay, cool. Okay, so first of all, let's import all of these libraries. Okay, I think I have all of them here, but let's just give me a second. Okay. I'm not gonna type them once again. So core libraries, we use this as usual for plotting, scikit-learn, DBSCAN, UMap, and okay. Why is it taking so long? Restart. Okay. Start. Let's run this again. Okay, everything's cool. Everything's cool. We have all the libraries. So first part is to open the GeoJSON dataset. So since it's a GeoJSON file, we're gonna use Python to open the file first. We're gonna open the file, okay? So the name of it is business locations.geojson, business locations.geojson, and we're gonna call it F, which is a file. So we're gonna define a variable JSON data, and we're gonna ask JSON library to load this file for us. So this is a JSON file for now. We can you can actually check some basic features. Num of features is, let's say we want to have the len of JSON data. We want to say how many data points we have within the data set, okay? And let's see, print an example. we're gonna ask JSON to dump one of the data points within our GeoJSON dataset. Okay, and let's increase the indentation to 2. Okay. What's the problem here? Missing one print. GeoJSON dumps. This must be dumps. Okay. So as we can see, we have 296 data points. An example of it is this, and we can actually like change the index and see another data point here. Okay, let's proceed. Now what we need to do is to we know that we are already more comfortable with NumPy and pandas while working with the data, so we have to actually flatten this data set because it's in the form of a JSON dictionary. To do so, we're gonna define a rows list, which is a Python list, and we're gonna say for feature, which is this feature means data point in the GeoJSON, like because here we have a features here. That's where the name comes from. For any data point here, we're gonna turn this into we have a props here, longitude and latitude, and here we're gonna append it. Okay, and we're gonna pass this by reference, longitude, latitude. Okay, so what is props here? We're gonna ask feature to give us its properties. You see, here we have feature and here we have properties. Okay, we're like reading this part of it. Okay, so we're putting this here, and for the latitude and longitude, we're gonna say, okay, feature, give us from your geometry, give us the coordinates, and let's check the namings. Coordinates here, yes. Oops, coordinates, yeah, okay. So this for loop gives us the JSON dataset into a Python list, and what we need to do is to just ask pandas to turn this Python list into a data frame. And to make sure that everything's done well, we're gonna run the usual command, which is asking for the shape of the data set, of that shape, and one row of it. Okay, as we can see, 296 rows, 10 columns, and this is first 5 rows. We have neighborhood, category, subcategory, floor area, square meters, daily foot traffic, community impact score, annual revenue, longitude, latitude. Okay, so we have the data set ready. You can also use info and describe to see what's happening within the data frame, but I'm going to pass it. So what we already know things about the data set. Okay, we already have names for these neighborhoods. Okay, but we might have some cases where we only have the coordinates without the neighborhoods names. Okay, so one way that we can use clustering is to find the density points. Okay, because we know like there are density points within the city where like the specific kinds of businesses are located and concentrated there. So if we don't know the neighborhoods, we can use clustering based on the coordinates to find these concentration zones. So from the dataset itself, I'm not going to write the code for these parts because these are already familiar for you, how we actually do it. I'm going to create two bar charts to show you the distribution of businesses per neighborhood and per category, okay? As usual, we're going to create them using matplotlib, and we've done it dozens of times, so there's nothing in it to do it again. So here we can see that we have a sort of an even distribution, okay? This is by intention. This is how we made the data set, okay? At the same time, so please pay attention to this column as well, because some businesses intentionally, they don't have any neighborhood in the data set. So if you actually use describe or info and search the data set itself, you can see that we don't have neighborhoods for them. It's blank. It's unzoned, okay? This actually also helps us to see k-means and other clustering algorithms in action together, okay? So if you need this code, and if you're following the lab with me, hopefully, I'm gonna just put the code on Discord, so you don't have to write it again. However, it's gonna take some time because I'm running multiple apps together on my device. And reply to additional resources, we have this code here. Let me actually create a thread here. Okay. Clustering the lab codes. I'm gonna put things here. Okay. Okay, we have a thread, and I'm gonna put it here. Ding. Let's go. Okay. Let's proceed. To see clustering in action, we're gonna check the business's location, okay? Based on their coordinates, okay? So I'm gonna just do this. I'm gonna say, okay, fig and x, I have a plot, subplots, fig size is 8 and 7. Okay. For name and group, I'm gonna have name and group and df that's group by neighborhood. Okay. We're gonna have a scatter plot group along, not groups, it's gonna be group longitude, group latitude, label name, okay, and the rest of the plot is like similar as usual, so I'm gonna just copy and paste it here. Okay, so based on the design of the dataset itself, we already expect the clustering to look like this. Okay, so we already have the cheat code because we have the names and stuff. Okay, what we're gonna see together is how our clustering algorithms based on the coordinates only can get us to this clustering result. Okay, so this is the ground truth. Okay, there are 4 dense roughly circular clusters which correspond to real neighborhoods, and there is a set of scattered unzoned points. You see we have these purple points here, they don't have any zones, so we want to see how each of the clustering algorithms treat these unzoned points. Okay, so a good clustering algorithm should find the 4 real neighborhoods and correctly recognize the scattered points as noise. Okay, we already know that these are noises. We don't want them. So we have 3 options. One of them is the k-means. The other is, DBSCAN, and the third one is HDBSCAN. I hope that by the end of the lab we can see these 3. Okay. So first of all, let me just scroll up. Okay. So first of all, we're gonna create a matrix based on the spatial clustering. Okay. So this is something new that you're gonna see. Okay. Unsupervised learning means that the learning structure from the data that has no labels, as you guys all mentioned. Okay, so first of all, we're gonna even normalize this this data that we have right now. Okay, we're gonna scale them. Okay, and the code here is how we do it. Okay, GeoFeatures, we are gonna select columns. This is pseudocode, but you're gonna see the exact code in a minute. Okay, so we're gonna have GeoFeatures, okay, which are coordinates basically, and we say we need longitude and latitude, and we need their values. Okay, based on this, we're gonna standardize them. Okay, so we're gonna define a scalar, standard scalar. This is based on the libraries that we have used. Okay, so we have a standard scalar from scikit-learn for pre-processing. Okay, we're using this scalar to scale. Oh, thank you so much. For longitude. Okay, have I made the same? Yeah, I have made this. So let me just do a quick Control F to see if I have made the okay, maybe the good idea was to proceed with the spelling. Okay, let's do that again. Okay, no errors. yeah, that's all right, that's all right. But where's the okay, longitude and latitude? Okay, yeah, sure. Okay, so we're gonna have the scaled based on the, we're gonna ask our scalar geo. Poor naming, guys, sorry, but this is our scalar, and this is the scaled data, and we're gonna ask it to kindly scale our geographic features, and we're gonna actually make a comparison here to see why we are actually doing it. Before mean was, and geo features that mean, the standard deviation was features that std 2, 3 floating points. Okay. After min is geoscaled, same thing, and std is geoscale, same thing. Okay, so we have moved them to another scale. I think I'm making it yeah, this is actually no. That's round. Both of them need to be rounded to 3 decimal points. Again, okay, yeah. Okay, so at this latitude, 1 degree of longitude covers a slightly different physical distance. Okay, so similarly, no, let's consider it as a sphere. Okay, so at a specific latitude, 1 degree of longitude covers a slightly different physical distance than 1 degree of latitude, and we standardize these to measure the distances in a more standard way. Okay, because like we're technically working with the sphere and we want to plane it on a 2-dimensional plane, so that's why we are doing it. We first start with the k-means. Okay, our first clustering algorithm is k-means. So first of all, we're gonna choose k, which is the number of clusters, and then we're gonna initialize centroids, which were the points we put on the plane that are starting points for our clusters. We're gonna assigning the steps, and we're gonna using Euclidean distance to find the distance of each point from centroids. And in each step, we're gonna move the centroids so that the mean of positions reduces until we don't see much of a difference when we move the location of centroids. But you're gonna see it visually. Okay, I'm not gonna just like tell you this on the air, but I'm gonna just show it to you visually. So we're gonna have a function to show us everything step by step. Okay, so we have x, which is our matrix. We have k, which is the k in k-means, the number of clusters, and then we have the number of iterations, the steps we're going to take, and the seed. Seed is actually the number we begin with to run the algorithm. Okay, if you're interested in what the seed is, I suggest you to search it, but I'm not going to explain it here because we're already short on time. Okay, so we're gonna use default setups. Okay, so we want a minimal k-means implementation. Okay, we're gonna give it the seed. Step 2 is to initial centroids. So we pick up arbitrary points over the plane to like just initial the centroids, k random data points. So we call it initial indexes. We're gonna ask our model to choose this number of points. We need this number of points. Okay, okay, and then centroids. Our centroids is the initial indexes dot copy. Okay, so we're gonna have a copy of it, copy of the matrix, and we're gonna put it in the centroids, and we're gonna have two copies of the centroids. One of them always stores the previous step. Okay, so history, we're gonna keep the centroids dot copy. We're gonna keep a copy of our centroids in the history. And for now, we don't have any labels. You will see. So we're gonna have a for loop. Okay. Number of iterations. Okay. We're gonna say we have like 4 steps of iteration, 3 steps, whatever. We're gonna run the algorithm. Okay. So first of all, we assign distance from every point to every centroid. Distances. Okay, this is the step where we calculate the distance from every point to every centroid. Okay, here gives us all the distances to each of the centroids. Okay, so here we say take each of the points and calculate their distance from each of the centroids. Okay, and then in the next steps, we're gonna update the position of centroids based on the previous step. Okay. Okay, so this here says for each of the centroids, okay, we have an index here. So if like we take the points which are centroids here, we calculate the mean. Okay, if the current number was higher than the mean, we're going to change the centroid position. Otherwise, we're going to keep it at its previous place. And then we're going to update centroids. And then we're going to append the list of centroids to the history. So the history is collecting the location of each centroid for us. We're going to use this function to just like create a cool visualization. Okay. Centroid history and manual. We're going to initialize it by step by step. Okay, so we have our matrix, which is geoscaled, which is X here, and for now we're going to say 4 clusters, because as we can see we have 4 clusters here, so we already know the clusters. But we're going to increase the number of iterations to 5, and we're going to put it to 0 for now. Okay, and let's print length of Centroid history. Okay, we expect the number of steps in history. Okay, we expect to see 6 history snapshots in this list. Okay, let's run it again. Why? Oh, okay, I made a mistake. That's it. Again. Okay, what's happening? Built-in function has no. Okay, let's see what's happening here. Centroid doesn't have any copy. Centroids. Why doesn't have? Okay, that's the problem here. Again, what am I doing wrong? Centroids. This must have a copy function. Let me see what I'm doing wrong here. So we're collecting distances using numpy. Argument. This is an array. Copy is missing brackets. I don't think so. No, it has the parentheses. This one here, yeah. This one here, yeah. That's it. Oh, okay, yeah. So the numbers, thank you so much. Yeah, that was the problem here. I was looking at elsewhere. So we have the number of steps here, and then we're gonna, like, together we're gonna see each iteration. Okay, so I'm not gonna write the code for visualization again. We're gonna just see it, and I also wrote the code to the function just to have a understanding of how the k-means work. Okay. Okay, so as usual, we're gonna say for each of the centroids in the centroid history, we're gonna have a scatter plot. Okay. In the first step, everything is in grayscale. For the next steps, we're gonna colorize it. Okay. And let's see this together. Okay, let me just put the code. Yeah, we're gonna see the visualization together in a minute. Just let me put the code to the visualization on Discord. As I had promised you, code to visualization. Okay, so this is it. At first, we had like 4 random points for centroids. In the first step, after 1 iteration, we updated the centroids, as you can see here, and the clusters are created based on their distance of each centroid. So this is the clusters that we have. We moved them again. Okay, so you can see actually, if I can zoom in, I cannot unfortunately zoom in. This is the, so yeah, you can see that we see a difference here on the border of pink and blue here. So there is a change, and here we can say that it has increased. You see the blue is coming towards taking the pink, and the blue is living, the dark blue is leaving light blue. Okay, so light blue is covering this cluster, dark blue is moving to the pink, and ultimately at the end, after 5 iterations, we see perfect clusters, which is really similar to what we already have here based on the dataset itself. Okay, so you can actually compare this. So this is actually how k-means works. Okay. Another thing is how we can use the k. Okay, so here we knew that after 5 iterations, we had the answer. But how do we actually use it? We have 2 methods. One of them is elbow method, and the other is silhouette. Okay, and the difference is elbow method plots inertia, and inertia is the sum of the square distances from each point to its centroid. Okay, so inertia is a decreasing function. Okay, so as k decreases, the output of the function, as k increases, inertia always decreases. Okay, but we're looking for a point where the difference between 2 points is like significant, and after that the difference between 2 points, it's really insignificant. So it goes this way, and there is a point here where we have a 1 point here, the next here, but the next one is like really close. They don't have like much of a difference. Silhouette, on the other hand, is like quite the opposite. It measures how similar a point is to its own cluster compared to the nearest other cluster. Okay, so we're gonna do this. I'm just gonna, like, you have the pseudocode here. I'm just gonna show it to you how we can do it. So first of all, let's define inertias, and we already have a hunch that we don't want to go over 10 clusters. Okay, this is an intuition we have just to begin with. Okay, we're gonna ask k-means library itself. Okay, we're gonna set the number of clusters to k. So random state, this is the number where we talked about, like we define it as a global variable here. So we're gonna put it equal to random state, and their number of initializations is 10. Okay, we're gonna fit it. We're gonna fit the model over the scaled data sets, and we're gonna update our inertia list. That append km dot inertia. Okay, same thing is for the silhouette score. Silhouette score is equal to it's gonna be a type of dictionary again, in range of 2 and 9. We're gonna ask k-means, of clusters. This is gonna be equal to k. Random state, and and we're gonna update silhouette score before. Can we get a quick summary of what we're doing right now? I just want to show you how elbow and silhouette works. Yeah. And then we're gonna do DBSCAN. We're gonna do different clustering algorithms together to see how they work. Yeah, I told you in the beginning. You will be doing the same thing. Like for your third assignment, you will be given a data set, and you will be doing the same thing to like get the K based on the either based on the elbow method or silhouette score. You're gonna run k-means, and I just wanted to show you how k-mean works, and you will be using these libraries the same libraries that we're using here. So yeah, I just wanted to show you so that you have seen it once. Okay. This is actually doing pretty straightforward things. So you see, let me just create the visualizations and then I will show you. Okay. Okay. So let me just explain it here. Let's run the code, and then it has I have a typo here, which is an S here, scores. Yeah. Okay, let me check if I still score. No results. Okay. Dict is not callable. What am I doing wrong here? Silhouette scores K is, why not? Let me see. This is the problem here. Okay, this is a function, not a variable. Okay. Tight layout. Tight layout. Okay. So there's a difference between k-means and silhouette, okay? And you can see the difference here, okay? Let me just, okay. You see, I'm trying to find a simple way to explain it. Okay. The way elbow method works is that it thinks that we have like 1, 2, 3, 4, 5 centroids on the plane. For each case, okay, it takes all of the points and calculate the sum of the square distance of each point to its centroid. Okay, so we have the centroid here. We take all of the points and we calculate the sum of the square distances from this point. Okay. On the other hand, silhouette, instead of taking the centroid and comparing all of the points in respect to this point, compares pairs within each cluster. Okay, so this is the difference between them. So silhouette actually measures how similar a point is to its own cluster, okay, compared to the nearest other cluster. So let's say if you actually want to do clustering based on the similarities, okay, it's better to use silhouette score instead of elbow method. Sometimes it's too scattered that silhouette score doesn't give you any meaningful outcome. Then it's better to use elbow method. Okay, but like you use these two to make sure that the number of clusters that you're choosing makes sense. Okay, so somebody tells you why, like consider the movie recommendation problem. Okay, if you want to actually cluster users based on the number of clusters, you should have a rationale for the number of clusters that you have. So this gives you the confidence to do that. That's essentially what I'm trying to show here. Okay. The last thing I would like to tell you, so if you are given a data set from scratch, you will be applying elbow and silhouette, as I have shown you here, to get the number of clusters, and then after you have the number of clusters, you're gonna just like run the k-means using the k-mean library in a second. But what I want to show you here is that k-means here doesn't do a good job addressing this unzoned points. Okay, so currently k-means is giving each of the points on the plane a cluster. However, we don't want to work with all the points on the plane. Okay, that's not what we want to do. Therefore, we will be using another method, which is DBSCAN. Okay, so any questions so far? No questions? Okay, I hope actually this is understandable, because I can get it. Sometimes it can get confusing, although I'm trying like my best to simplify what we're doing here. Okay, so next part is to do k-means. Okay, so we saw that k-mean, the downfall of using k-mean is that there are points on the plane that are assigned to a cluster, which we don't want to work with. Okay, we want clusters, we want meaningful clusters. So if somebody asks us, why is this point in this cluster, in the light blue cluster, we say only because the algorithm has given us this, although we don't want to work with these. So the alternative is to use DBSCAN. So DBSCAN is actually density-based spatial clustering. Actually detects noise, because instead of like having a centroids, it defines core points. Okay, so we have core points, we have a radius to see whether other points are in the radius of that core point, and if a point is not within the radius, it's going to be considered as noise. So we will like randomly choose points over the plane. Okay, we will add all of the points within the radius to this cluster, and then we repeat step 2 with moving the core point so that the cluster grows. At the end, where we have visited all of the points, we stop the algorithm. Okay, so we choose centers, we increase the radius, we observe the cluster. When we reach to a point where all of the points are visited, we stop the algorithm. Okay, some of the points might be visited during this exploration, but they might be labeled as noise. Okay, so their distance from this core point will be set to -1. Okay, so let's see it in the action. First thing is, let me put this on Discord, on the thread. Yeah, how DBSCAN works. Okay. So the trick here is the radius. Okay, we're choosing core points. We are exploring the points that are within the radius, and the trick here is to how we should find this radius. Okay, because it's not trivial to find it. To do so, we're gonna pick minimum samples. Okay, so it means let me put it this way. A standard trick for choosing the radius, EPS, is to compute for every point the distance to its minimum samples nearest neighbor. Okay, so we take this, we draw we want to see after how many steps with the length of epsilon we can reach to the core point starting from any point. Okay, I think I'm not explaining it really well, but let's see it together. Okay, as you can see here, the pseudocode says we set the minimum sample here to 5, equal to 5. Okay, let me just clear these. So we have a model which traverses neighbors model. We say, okay, so you check the number of neighbors, which is equal to minimum samples. Okay, we have set the minimum sample to 5 here. We change the minimum sample and see how it changes together. Okay, then we ask the model to fit over geo-scaled matrix, which consists of our coordinates, and we're going to have distances k neighbors geo-scale. Okay, so we're going to calculate the distance by telling NumPy, please sort distances in a ascending way. Okay. Okay, distances. Okay. So, we're choosing a point for like different radiuses. We're gonna measure the distance of this point to its 5th nearest neighbor. Okay, and we're gonna sort them, and we're gonna see where our diagram like breaks and goes into ascending, increases the slope. And similar to the elbow here, you see, in the elbow here, we watch the slope, where the slope is like really increasing highly. We pick up a point from which the slope doesn't increase strongly. Okay. The similar is here. We are observing this diagram here, and we want to choose a point here where the diagram goes ascending, like the slope increases quickly. Okay, so this will be our epsilon, the radius that we're going to use for DBSCAN. If we change the minimum sample, like let's say to 7 or 8, let's see, no, let's change it to 2. Okay, it doesn't make a difference that much. So in this case, we have like a pretty normal distribution. But this is the way of finding this radius for DBSCAN. Okay, and most points sit on the flat part to describe this diagram. Flat part of the curve. These are dense neighborhoods. Okay, small distances. But the curve shoots up sharply for the last 20 points, and these are the noise points. Okay, so if we pick the radius to be 0.22, the points that are far away from this distance, there will be noise. Okay, and then we're gonna ask DBSCAN to find the number of clusters for us based on the given parameters, and then run the model for us. Okay, so I'm gonna define a model, DBSCAN, and I'm gonna say, okay, I have decided to have my radius equal to EPS equal to 0.22, and the minimum samples, the minimum of the points that you have to traverse before deciding whether a point is noise or not, is equal to 5. Okay, and then I want my data frame to be fit, like I want to fit the model over the geo-scaled version of dataset that I have, and I'm going to put it in a new column, DBSCAN cluster. Okay, so I'm adding another column to the data frame. Number of clusters, DBSCAN. Okay, I'm gonna say, okay, please give me the number of clusters based on the model that you have fitted here. Okay, so I'm gonna say, what's the length of this column, DBSCAN cluster. Length of this one. Okay. Okay, we create the model, based on these parameters. We run the model, we add another column to the data frame, we get the number of clusters, we get the number of noise points, and then we're gonna see it together. Let's see. Okay, this is what I'm doing wrong. What am I doing wrong? I think the problem is with the parentheses here. I'm saying, oh, okay, the data frame where the DBSCAN cluster is equal to -1. I want the sum of them. Again, okay, let me check. DBSCAN for predict geoscale, number of clusters, length of this. Okay, set. Yeah, are you sure? I'm not. Where do you mean no? Oh, yes, that's it. Great. Thank you, guys. Thank you, guys. Yeah. That was the problem. Again, I was looking at it in a wrong place. Thanks. Okay, so yeah, cool. Okay, yeah. So just let me explain what we've done here. Okay. This formula here might be a bit of confusing. Okay, so I'm just gonna explain it part by part. So this one here, it collects all the unique label values that appear. Okay, and then we know that if if it's equal to -1, it's a noise. Okay, it's not a real cluster, it's a noise flag. So we're gonna put it away. Okay, and there's a conditional expression that it's equal to 1 when the noise is present, it's 0 when there's no noise at all and there's nothing to subtract. Okay, and this technically so it takes the number of different items within this column and takes out all of the -1s. This one says, okay, give me all the rows where DBSCAN clusters is equal to -1, which actually points out to all the points that are noise, and we need the sum of them, which is equal to 20. Okay, yeah. And if we want to see it visually, it's 8:10 p.m. Okay, and if we want to see it just visually, we can do it as usual. So we have figure and we have axis, plot dot subplot, figure size is equal to 87. Noise mask, we want to put a cross mark over the points where we have noise. DBSCAN cluster where it's equal to -1. We have a scatter plot. We're gonna okay, we're gonna take the points that are not noise mask and their longitude. again, not noise, mask, and latitude. What else? Okay, Minaho, write down. Okay, no. It's related to the error we have. Okay, I thought that you had sent a new message. Okay, where were we? Okay, color is equal to df log noise mask and DBSCAN cluster, DBSCAN cluster, CMap, no. Okay. Okay. Let me double check. Yeah, cool. So this parenthesis is closed and we have all the commas, okay? And for the points that are noise mask, location, let me just copy paste this. Light gray. This to X. Okay. Okay, cool. Let me just Okay, so DBSCAN was able to detect noise points while clustering our points, and we can like compare it to, let me see how we can compare it to, where can I have an empty canvas? Let me see. Okay. Let me copy and paste this here. Alright. And the original one, where was the original one? Okay, here, let's copy this. Okay, let me see if we can do this. Okay. It's not really easy, but if we this is the original one that we had, okay, based on the original data set, and this is the result that we have based on the DBSCAN. We can see that it's done a really good job in detecting noise, with some like exceptions. This is supposed to be noise, but here it's not noise, and this one also supposed to be a noise, but yeah, here this one's supposed to be a noise, but here's not a noise. So DBSCAN is actually like way more powerful when we have noise and we want to put them aside. Let me make this smaller. Let's see what happens. Yeah, it's easier to see them here. We can, oh no, sorry. We're supposed to come here. Yeah, here. One thing that I would like to do is to, oh, no. Okay. One thing that I like to do is to change the numbers here, like the minimum samples and the radius here, and to see how our diagram would be different here. Okay, so just give me a moment to see this together. Okay, so I want to increase the number of the walks. Okay, so instead of like considering the distance to the 5th nearest neighbor, I want to increase it to the 8th nearest neighbor. Again, the chosen radius would be equal to the same number, but let's change this and see what happens. Okay, we can see that same thing applies, same thing holds. What if we increase the radius? Let's say put it to 0.4. Okay, we can see that we have 3 clusters this time. Okay, we have 3 clusters and we have less number of points. Why? Because let's consider this cluster here. Okay, DBSCAN has chosen a point here as the core point, okay, and has gone as far as 8 neighbors with a radius equal to 0.4, and has came to this conclusion that all these points here, they belong to the same cluster. Well, let's do this. Let's say if we put the minimum samples to 3 and run this again, we reach to the same conclusion. But here, these noise points, actually, they become a cluster themselves. Why? Because we said, okay, it doesn't matter if you are just like 3 points here. I have decided to only check samples with 3 members. Okay, so 3 members with a high radius, with a high walking lane, has resulted into creating a new cluster here. Okay, so what I wanted to do here, just to show what these numbers mean in terms of like the different outputs that the model can give you. Let's say if we decrease the steps, if we decrease their steps to say, let's say 0.05, and then run this again, we can see that we have numerous clusters. We have 17 clusters, and it doesn't actually make sense. Why? Because we have like lots of close points here, which technically need to like be under the same cluster, but they're not. And we have lots of noise points, which again, it doesn't make sense to have this many noise points, because clearly we can visually see that these are supposed to be within the same cluster. Okay, so this minimum samples, this actually comes, like if you are working with a small data set, this comes from your own intuition. Okay, let's say here we know that a neighborhood with like 5 businesses, it's not such a dense neighborhood, or it cannot be considered as a center of concentration where people would like to have like new businesses. Okay, but this radius here, this radius, it needs to come from actual calculations. Okay, which we derive it from here. We should derive it based on this k distance plot. Okay. Okay, we're technically done for the lab. I also wanted to show you DBSCAN, but we couldn't make the time. And we didn't actually have the time to check dimensionality reduction. I might create another video to show you the dimensionality, because that's a more abstract concept, which is harder to understand with no visual presentations. So, any questions? Since we're at the end of the lab, any questions? I know it was a bit of hasty. Yeah, it was a bit of hasty because like I wanted to show you some details while covering some topics. Matt, this is all good. I hope for the rest of you guys it's all good as well. Before your third assignment, you will have another video explaining some of these concepts. Will we complete the rest of the code in the next lab or lecture? It doesn't actually make sense to complete the code as a lab task, 1. 2, you're gonna have your third assignment released, I think by tomorrow, which is really similar to this one. However, in the next 2 or 3 days, I try my best to either record a video for the rest of the lab, which was dedicated to dimensionality reduction, or your assignment would have enough time that we can cover the rest of this lab next week. Okay, it's one of these two, but you're not required to do a lab task because your third assignment is technically like doing the same thing, similar thing. I just wanted you to see the data set, how the k-means work, how the DBSCAN works, and with that we've been successful. All right then. It seems that you don't have any